So numerical solutions of ordinary differential equations. That's what we are going to discuss. This is the last part of numerical methods. So analytic solutions we have done when we did differential equations. For differential equations of higher order with constant coefficients, and for linear differential equations there are so many methods: variable separation of variables, homogeneous form converted to separation of variables, and linear differential equations, and also by inspection exact differentials we can form and solve. Now they are very, if we compare the infinite possibilities of functions, there are only very limited functions or limited differential equations for which we can actually solve the differential equation. So solving the differential equation by those steps of any of the methods that we discussed, they are analytical methods, and they give exact solutions, or we call them as the analytical solutions. Okay. However, for most problems, for most engineering problems, it is very difficult to find a analytical solution. Okay, because there will be complex integrals. There will be complex integrals. Now, so to find the integration is very, very difficult. So now there are various numerical methods. So this is the differential equation. Okay. Now we can get any of the ordinary differential equation of the first order in this form. Dy by dx is some function of xy. This can be whatever. And if we know that at x equal to 0, the function gives y equal to 0. So if we know these two things, we can solve. So so there are methods. What we will discuss first is we will be discussing three methods basically: Euler's method, modified Euler's method, and Runge-Kutta method for solving the differential equation. Okay, so let me so numerical method, numerical solution for ordinary differential equation. So a number of solutions are available. And I'm not going into detailed classifications. Okay, now let us start with the first one, Euler's method. There's a picture graph I will draw. This graph I will draw. Okay, I'll explain directly. Euler's method. So, first one is Euler's method for solving the ODE. So, when we say solution of an ordinary differential equation, we mean that we have to find that function y equal to f of x that satisfies the differential equation. Okay. So, that particular function which satisfies the differential equation, I'll instead of f of x, I'll write p of x here. Now, given the ODE is of this form, dy by dx is f of x comma y. That's why I chose p of x instead of f, because it's the standard way, where function y is a function of x. So at x naught, the value is y naught. Given this, we have to find. So let us say we want to find an approximation. So let us consider the solution. Let's say this is x and this is y. And let us say that this is the function. Let me put a full curve. That this is the actual solution. Okay. Now, given to us that one point at x equal to 0 and draw straight lines. Okay. This is x equal to 0. And this point, let us call as P. Now, P is x naught comma y naught. This is what is given to us. Now, starting from here, I need to find out the next solution, the next step. So I will not be able to find a numerical solution. I will not be able to find a full curve, but I can find points on the curve, like say x1, y1. Okay, this is the point P2. P1. Then the next one. So how do I proceed? Suppose I want to find the next point. See, if I can find some 10 or 20 points on the curve, then from there I can do interpolation and I can establish what the curve is. Okay. So what we do is we want to find out what this point P1 will be. P1 should be x1 comma y1. So now depends on how many points do we want. Okay, so let the solution be a curve through. Let the solution be a curve through P x0 comma y0. Now consider the subintervals. Consider the subintervals. X is x0 plus k minus 1 times h and x0 plus kh. That means for k equal to 1, 2, 3 up to n. So what are these intervals? So x varies. We are considering intervals, subintervals. The first interval, when you put k equal to 1, you get x0. X lies from x0 to x0 plus h. So this interval width is considered as h in a different color. This interval width is h. x0 to x1, the interval width is h. We know this point, we are trying to find what is the next point. So for k equal to 1, that is what we are doing. For k equal to 1, x lies between x0 and x0 plus h. Okay. Now let P1 be equal to x0 plus h comma y1. This is x1 comma y1. x1 is x0 plus h comma y1. That means at this point the function value is y1. Okay. Now how to find this y1? So let us say this this coordinate is x0. I will mark this point on the x-axis as L, this as L1. Okay, so value of y1 here, if we solve y1, we have got the point, we have got the solution. So y1 is L1 P1, correct, which is equal to LP Okay, LP. Now, suppose I draw a horizontal line here. Okay, let this point be R1. Okay, so I get this as L1 R1 plus R1 P1. This L1 R1 is nothing but equal to LP plus R1 P1. Correct? Now, this LP is nothing but Y0. So, therefore, Y1 is Y0 plus R1 P1. Now, if you look at this, I'm drawing here, this is P. At the same level, it is R1. And let's say next point P1 is here. Now, how do we find P1? How do we get approximation of P1? We are making an approximation now. What we do is we draw a tangent at P. We draw a tangent at P. So I'm showing the tangent at P. Now, purposely, I'm not showing that it exactly coincides with P1. P1 may be the solution exactly on the exact curve, but we are making a numerical approximation. So what we assume is that instead of the original point here, P1 is this point at the end of the tangent here. That is the Euler's method, end of the tangent. Now the tangent at this point makes an angle of theta with the x-axis. This is parallel to x-axis, so it makes an angle of theta with the x-axis. So in that case, what do we get is tan theta is P1 R1 by PR. What is PR? This distance PR1. PR1 is this distance, that is equal to the interval width h. So P1 R1 by h. So therefore we get P1 R1 is equal to h times tan theta. So what we get is Y1 is equal to Y0 plus h tan theta. Now tan theta is the slope of the tangent, which is, dy by dx at P. Dy by dx at P, correct? Now what is dy by dx? Go back to our original differential equation. Dy by dx is f of x comma y. What is f of x comma y? It is some relation between y and x's, because the differential equation can contain the dependent variable and the independent variable. Okay, and dependent and independent variables are related with this function p of x. Okay, but on the right hand side of dy by dx, we get some combination of x and y. So dy by dx we know is this expression. So this is h of f of x comma y at P. What is P? X0, Y0. So we get, this is Y0 plus h times f of X0, Y0. Just a moment. Okay. So y1 is y naught plus h times f of x naught y naught. So this is the iteration step. So I knew at x naught value is y naught. From that, from the given equation, I have got a numerical approximation that the next solution point. So solving a differential equation for us means finding all such points on the curve. So if h becomes very, very small, we'll get, let's say h is made 0.001. Then, so for every iteration step, you will find the function value. So you will get, when you plot, you will get a function plot. So solution of numerical solving of differential equation is finding these points P1, P2, P3, P4, P5, so on. So Euler's method means in every interval, I take the lower limit, take its slope of the tangent, and find the value using this f of x comma y, and use this approximation that tan theta is this additional value upon the interval width. So I get this value. To that I add the original function value. So for the next iteration step, we have to do the same thing. For the next iterative step, for x2, again I find the tangent. Okay, I'll use a different color here. And the same value here. This will be R2. This is L2. So let us do this. For next iterative step. Iterative means we are repeating the process. That is, for k equal to 2, we get x lies between x naught plus h to x naught plus 2h. So we want to find y2. Y2 will be L2 P2. Correct? L2 P2. That will be equal to L2 R2 plus R2 P2. This is L2 R2 plus R2 P2. And this L2 R2 is same as L1 R1. No, it is not as L1 R1. It is L1 P1. L1 P1 plus L1 P1 plus this R2 P2. So L1 P1 is Y1 that we found from the previous step. L1 P1 is Y1, which the value of which we found from the previous step. Next, again the same. This is P2. Now we assume that the tangent theta, this is H. So R2 P2 is H times tan theta. Which is now H times, this is tangent at P1, right? So tan theta is dy by dx at P1. So we get y1 plus h times dy by dx is an expression of x, f of x and x comma y. So at P1, you will get f of x1 comma y1. So this is y2. Look at y1 step. Y1 is y0 plus h times f of x0 y0. Y2 is y1 plus h times f of x1 comma y1. Therefore, in general, for nth step or ith step, for yi plus 1, yi plus 1 is equal to yi plus h times f of xi y. This is the Euler's method of finding the solution. This you have to remember. This is Euler's equation. So this is the iterative equation. To solve ODE. So once you know this, you keep solving and you will get the result. Okay, let's do an example. I'll give an example here. I'll explain this example. Wait a second. Now, yeah, okay. So this will explain to you the calculations. So using Euler's method, find an approximate value of corresponding to x equal to 1, given that dy by dx is equal to x plus y and y of 0 is equal to 1. That means when x equal to 0, y equal to 1. So this is given to us. Now, it has not been specified, but suppose we take n equal to 10. That means, see, I know the value at x equal to 0. I want to find the value at x equal to 1. Now, if I directly take the step as 1, I will get a very big error in the answer. Okay, because it's a curve like this. All right, and here I take this slope. According to me, this should be y1, but in the function, in the real actual function, this will be the value of y1. Okay, so then there'll be a big error, na? So that's why we divide this into a number of intervals. So between x equal to 0 and x equal to 1, let us say I am taking 10 intervals, n equal to 10. That means 10 substeps. So h will be whatever the value we want, the next step we want from the given step by 10. Okay, so it is 0.1. So h, the interval width, is 0.1, which is sufficiently small. If you want to make it 100, n equal to 100, this will be 0.01. Then you will have to use a computer program and immediately it will solve. But in the GATE exam, we will have to do steps. Now the various calculations arranged as follows. First, this is x1, not x0. This is x2. This is x3. This is x4. Correspondingly, this is y1, y2, y3, y4. This is, sorry, this is x0, this is x1, x2, x3, typo error here. This is 0.0. Okay, so x1, x2, x3, 0.01. So dy by dx is f of, this is our f of x comma y. And what is Euler's? Write down the Euler's iterative step. yi plus 1 is yi plus h times f of xy. So Euler's iterative step, yi plus h times f of x comma y is x plus y. So you get xi plus yi. So this is the iterative step. So this x plus y is dy by dx. Okay. So now what this statement is, yi plus 1 is equal to yi plus h times, okay, dy by dx. So this xi plus yi is calculated here. So on the first step, x0 plus y0 gives 1, because for x equal to 0, y equal to 1, you get 1. Now this is y0 plus h times dy by dx. Okay, so when you substitute this, y1 is y0 plus h times x0 plus y0. y0 is 1, h is 0.01, 0.1, x0 is 0, y0 is 1, because the original x0 y0 point is 0, 1. So we get this. So this is 1 plus 1 into 0.1 is 0.1. So I get 1.1. That is what we get the first step. Next, this becomes the next iterative point. So So this 1,1 is copied here because this becomes y1. So now y2 we have to find is y1, that is 1.1 plus h 0.1 times dy by dx, that is x plus y. X plus y is 0.1 into 1.1, it is 1.2. So multiply this becomes 0.12. So when you add, you will get 1.22. So the same step is repeated now. This 1.22 is your y2. Now x1 plus x2 plus y2 is 0.42. The next step is y2 plus h times x plus y, that is 1.42. It gives 1.36. So like that, if we calculate, when you reach 1, you get 3.18. This is the answer. So the approximate step is 3.18. If we go 10 steps like this. Now, what is the exact solution? We remember dy by dx is equal to x plus y is a linear differential equation. How do we write? Dy by dx minus y is equal to x. This is of the form dy by dx plus p of x times y is equal to q of x. What is the solution? Integrating factor times y is equal to integral of q times the integrating factor dx plus c. What is the integrating factor here? E power integral p of x dx. E power, now here p of x is -1. Integral of -1 dx is minus x. So integrating factor is e power minus x. So solution is y equal times integrating factor is integral of times x dx plus c. So first function integral, okay, first function is x, annihilate. First function into integral of the second, minus derivative of the first, that is 1, derivative of the first function is 1 into integral of the derivative of the first into integral of the second. This is minus x e power minus x minus of e power minus x plus c. So y see what is the solution. Is minus x minus 1 plus c times e power x. Okay, now given that at x equal to 0, y is equal to 1. So substitute y equal to 1, x equal to 0, e power 0 is 1. So we get c is equal to 2. So we get y is minus x minus 1 plus 2 e power x. So this is the exact solution. Solution by linear differential equation is, yeah, we are comparing, for comparison's sake, we are doing this. So y is 2 e power x minus 1. Okay. Now, so this is exact solution or analytical solution. Okay. Now, at x equal to 1, y value will be 2 e power 1 minus 1 minus 1. So 2 into e, let's take the calculator. Two times e minus 2 gives 3.43656. We'll truncate at 3 decimals. So 3.4365, so 437. 3.437. Truncating. 3.437. What did we get by Euler's method? 3.18. So we got error because we took the solution step as 0.1. If we take as 0.01, it will come close to this 3.437. It will be still error. Only when h tends to 0, you will get the exact value. So this we are comparing the numerical solution with the analytic solution. In this particular case, we could find an analytic solution. It exists. That's why we are taking this example. However, in many problems, you won't get the analytic solution. Then we have to depend on this. The lesser the size, more accurate is the result. But sometimes what happens when the size goes very, very small, there is a chance to get into an infinite loop. So there's a whole discussion on numerical methods. We won't go into detail, but for gate point of view, this basic information is sufficient. So this is the Euler's method, in which this is the iterative step to solve for the equation. Okay. So next we move on. Here, for example, to solve this, we have to do this example by Euler's method. To solve this, homogeneous differential equation and all you can solve, but let's say this is not solvable, then we use this method for Euler's. Now, modified Euler's method. Now, what we say, you observe this very carefully. Actually, there is one in between Euler's method. We are not using that. I'll explain this. See, the target of changing methods is in less number of steps, I should get more accurate result. I need not make this h very, very small. Without making this small, I should get accurate result. So that is why all these different methods. So now in one step size, just a second. Okay. So in Euler's method, what we assumed was this term we get by using the slope at x1. This is xi, this is xi plus 1. So for the next step, I want yi plus 1. What we do is we take the slope at this point. Okay, slope at this point and then approximate this slope at. Now we say, okay, there will be error because of this. So what modified Euler's method does is I will consider slope at yi plus 1. Okay, this is unknown to me. This yi plus 1 is unknown to me. Okay, but I will try to find the slope at yi plus 1 and approximate this. Instead of approximating the slope at y1, I am taking slope at yi plus 1. Okay, now this is unknown to me right now. So, but the slope at yi plus 1 is f of xi plus 1 and yi plus 1. So I substitute this. Now I get an equation. I get an equation now, a relation in terms of yi plus 1 and here also yi plus 1. Xi plus 1 I know, yi I know. So I have to solve now. I have to solve yi plus 1. Okay. So this is called backward Euler's method because I am using the slope at yi plus 1 and this is an implicit method. Implicit in the sense, why we say implicit? I want to solve for yi plus 1, but the same yi plus 1 comes in the step that I want to solve. In Euler's method, it was very easy. I want yi plus 1 and from the previous step, I know yi. So it is just a forward calculation. Okay, I know yi. From there, I can find yi plus 1. But here, for the iterative step, I am getting a function which contains the value of the iterative step. So I will have to solve. So for example, in the previous question, for the previous question, f of x comma y was x plus y. Correct? So how does the backward Euler method iteration look? I get yi plus 1 is equal to yi plus h into xi plus 1 plus yi plus 1. So what I do, yi plus 1 will be 1 minus h. 1 minus h. This equal to yi plus h times xi plus 1. And xi plus 1 we know is x naught plus xi plus plus h, correct. So yi plus 1 is 1 by 1 minus h times y1 plus h times yi plus h times xi plus h square. So we get this approximation. So I have solved y1 yi plus 1 is defined in terms of yi plus 1. So this is called as an implicit iterative step. Hmm. So backward Euler's method is an implicit method, whereas Euler's method is an explicit method. Explicit means by I plus 1 is explicitly, it appears only on the left hand side of the iterative equation. It doesn't come on the right hand side. Okay. In backward Euler's method, we need to rearrange and solve one for yi plus 1 before proceeding further. So this is backward Euler's method, and sometimes it is very effective. It is better than the Euler's method. Okay. There is an intermediate method which we have not gone for modified Euler's method. There's an intermediate method in which instead of taking slope at y1 and slope at yi plus 1, we take the average of the two. We take the average of the two methods, the average of the two slopes, and then calculate. That means this dy by dx is taken as the average. It is dy by dx. Here h times dy by dx at p is taken as f of x naught or xi yi plus f of x I plus 1 yi plus 1 by 2. So that approximation is also done. Okay. But this is partial. Again, this will have a back substitution to do. So numerical methods is very interesting topic in solving for differential equations, and more advanced numerical methods for solving differential equation is the finite element method. That is more advanced. This is just a iterative step. Now, next, let us move forward. Okay, the same backward Euler's method, the same thing, corresponding to x equal to 0.2, use step size 0.1. So in 2 steps we have to calculate. Okay, so now we have what is called as the Runge-Kutta method. Okay. So modified Euler's method develops into Runge-Kutta method. When you increase the order, all right. So Taylor series method of solving differential equations numerically is restricted by labor involved in finding higher order derivatives. However, there's a class of method known as Runge-Kutta methods which do not require the calculations of higher order derivatives. These methods agree with Taylor series solution up to n terms. We didn't go by the Taylor series method. In Taylor series method, what we do is this dy by dx. In order to find, we write a Taylor series and do an approximation. That will have its own issues. So now these methods agree with Taylor series solutions up to the terms in H, where H differs from method to method. Euler's method, modified Euler's method, and Runge-Kutta methods are Runge-Kutta methods of first, second, and third order respectively. We'll see what this Runge-Kutta method is. The fourth order Runge-Kutta method is most commonly used as Runge-Kutta method or classical Runge-Kutta method. Okay, how to find? Okay, there is a missing link here for Runge-Kutta. So I will write here note. Runge-Kutta method of first order is the Euler's method. There it is of the first order. Why? Because you are just multiplying with H in the first order. But here in the second backward Euler's method, you get H square. It is the second order iteration. So Runge-Kutta method of second order is modified Euler's method. Then Runge-Kutta method of third order is Runge's method. Okay. Now, see, there is a way to compute. So, in Runge's method, what is happening is this. Okay, in Runge's method, we need to solve dy by dx is equal to f of x comma y. Now given y of x naught is equal to y naught. That is, we know this x naught y naught point. Now let the next step be, say x naught plus h is equal to x1 comma y1 is x naught plus h is equal to y naught plus k. So what Runge's method does is, say this is x naught and this point is y naught, and when we have to find this x naught plus h, this is on the x-axis, these points. These points are on the x-axis. So this is x naught plus h here, and this is y naught plus k. Now how to find this? So how to reach this point? Function value and the slopes may be different. So what Runge's method does is, I don't consider this linear. I'll consider it quadratic. I will take another point in between, which is exactly half of it. Okay, this is x naught plus h by 2. Okay. So this is x naught plus h by 2. So there are some iterative steps. So I use some iterative steps. First, so I will use, the Simpson's rule to integrate here. If I use the Simpson's rule, Simpson's 1/3 rule, or like that, then I get this k like this. K1 I get as h times f of x naught y naught. K2 will be h of f of x naught plus h by 2, comma y naught plus h by 2, y naught plus k1 by 2, k1 here. I'm using k1. Now k3, there is a iterative steps in between. We'll get to the final result. Not k3, k dash, and in between k dash is equal to h times f of x naught plus h, y naught plus k1, and k3 is h of x naught plus h, comma y naught plus k dash. So now finally k is computed. We want k, right? Y naught plus k. Now k is computed as 1/6 times k1 plus 4k2 plus k3, just like in Simpson's rule. So y1 is y0 plus k. This is y0 plus 1 by 6 times k1 plus 4 k2 plus k3. You have divided it into subintervals. Subintervals, and what you have done, taken the average of slopes here, average of slope here and average of slope here, and then average of slope here and average of slope here, and then done it. That is why we get something like this. Okay. So this is the Runge's method. This is Runge's method. Now, for Runge-Kutta method, so we want to find y1 is y0 plus k. We have to find this k. For this, first step is k1 is h times f of x0 y0. Next, k2 is h times, like Runge's method, x0 plus h by 2, comma y0 plus k1 by 2. Next, k3 is h times x0 plus h by 2. This remains common. This becomes y0 plus k2 by 2, the previous step. Then k4 is h times f of x0 plus h y0 plus k3. So easy to remember. This is much better than the Runge's method. x0 plus h by 2, y0 plus k1 by 2, the previous step. The third step, x0 plus h by 2 plus y0 plus k2 by 2, the previous step. The last step, fourth one, x0 plus h, y0 plus k3. So this. Now finally, k is taken as 1 by 6 times k1 plus 2 k2 plus 2 k3 plus k4. So from there, we can find the next iterative step. So we may think, why so much calculation from one step to another? To get accuracy. Okay, we need to get accuracy. So when we use computer programs to solve, this becomes very, very easy. So in general, this is the Runge-Kutta method. In general, yn plus 1 is equal to yn plus k, or I will use the regular iterative step I. yi plus 1 is equal to yi plus k. All right. For xi plus 1 is equal to xi plus h. Now where, how to find k? K1 is h times f of h of f of xi comma yi. Now k2 is h times f of xi plus h by 2 yi plus k1 by 2. K3 is h times f of xi plus h by 2 comma yi plus k2 by 2. This is the sequence. K4 is h times f of xi plus h y comma yi plus k3, and k, this k is 1 by 6 times k1 plus 2k2 plus 2k3 plus k4. So this is the method. This is the Euler's method here. Sorry, Runge-Kutta method, which is the fourth order. So let's take an example. We will do this. So same problem that we have done. Fourth order Runge-Kutta method. So apply Runge-Kutta fourth order method to find an approximate value of y when x is equal to 0.2. Given that dy by dx is x plus y and x equal to 0, when x equal to 0, y equal to 1. So h value we are directly taking 0.2. So unlike Euler's method, we don't have to do x naught is 0, y naught is 1. Now h is equal to 0.2. So therefore x1 is x naught plus h is equal to 0.2. To find y1 is y naught plus k, which is 1 plus k. This k we have to find. So using Runge-Kutta method. Now using Runge-Kutta method, now what we do? First one. So f of x comma y is this dy by dx is f of x comma y is x plus y. All right. Now k1 is h times f of x naught plus y naught, f x naught comma y naught. So this is h times x naught plus y naught. H is 0.2, x naught is 0, y naught is 1. So you get 0.2 K1. K2 is h times f of x naught plus h by 2, comma y naught plus k1 by 2. So this becomes h times the sum of x and y coordinates, right? So f of x comma y is x plus y. So it will be x naught plus h by 2 plus y naught plus k1 by 2. So when we calculate, substitute now, h is 0.2 times x naught is 0, h is 0.2 upon 2 plus y naught is 1 plus k1 by 2. This is k1. So we get 0.1 plus 0.1 is 0.2 plus 1. So 1.2, 1.2 into 0.2 is 0.24. Let us find K3. H f of x naught plus h by 2, comma y naught plus k2 by 2. H times x naught plus h by 2 plus y naught plus k2 by 2. 0.2 times 0 plus 0.2 by 2 plus 1 plus k2 is 0.24 by 2. This will become so I'll use the calculator here. So this is 0.12, 0.24 by 2. So I get 0.1 plus 1 plus 0.12. This I get 1.22 into 0.2. So 0.244. See the approximation. If it is just Eilers, you will get K1 as 0.2. But the next step, it is 0.24, 0.244. The last step we will see. H times f of x naught plus h, y naught plus k3, which is h times x naught plus h plus y naught plus k3. 0.2 times 0 plus 0.2 plus 1 plus 0.244. So when we calculate this, so 0.244 plus 1 plus 0.2 into 0.2. So 0.2 888. Now K is 1 by 6 times K1 plus 2 K2 plus 2 K3 plus K4. It has to be a weighted average. Okay. Why 6? Because 1 plus 2 plus 2 plus 1 is 6. So weighted average we are taking. Now K1 is 0.2. K2 is 0.24. K3 is 0.244 and K4 is 0.2888. Let us calculate. So now 0.244 into 2 I am doing. So 0.488 plus this one 0.2888 plus this is 0.48 plus 0.2. So you get 1.4568 divided by 6. So 0.2428. Therefore, y1 is y0 plus k, which is 1 plus 0.2428, which is 1.2428. This is the Runge-Kutta method. So let's compare 1.2428. Now, let us compare with the value we got by the Euler's method for 0.2. For Euler's method, we got 1.36. Okay, y2 value. So, but here we are getting 1.2428. So that's the difference for the same result. So let's try to do some numerical problems. Okay, here. So Euler's method. So very clear the solution here. Okay. So backward Euler method for solving. This is a differential equation is specified by this step. So yi plus 1 will include, so yi plus h times f of xi plus 1 plus yi plus 1. So this is the solution. This is the Euler's method. This is backward Euler's method. Backward Euler's method. During the numerical solution of the first order differential equation using Euler's method with step size h, the local truncation error is of the order h square. Clear? Because it is a linear of order 1. So error will be in the order of h square. So for modified Euler method, it will be h cube so for Euler method, it is h square. Okay, this is h square. Next. Okay, this is on Euler's method. This is same x plus y, whatever we did the problem. Consider a differential equation dy of x by dx minus y of x is equal to x. With the initial condition y naught is equal to 0. Only initial condition is changed. So this is same dy by dx is equal to x plus y. We can do this. Use step size of 0.1 and the value, find the value of y equal to 0.3. So again, we will write these steps. This is xi, this is yi, this is dy by dx is equal to f of x comma y, which is x plus y here. So y of Euler's method is asked first order. So y of I plus 1 is yi plus h times f of xi yi, that will be xi plus yi. So I equal to 0 now first. So x naught is 0, y naught is 0. So y1 will be y naught plus h step size he has given 0.1 is 0 plus 0. This will be 0. Now next, the next step size will be 0.1. Now y1 is 0. y2 will be y1 plus h times x1 plus y1. Okay. Now y1 is 0 plus 0.1, x1 is 0.1 plus 0. So this is 0.01. So y2. So x2 is 0.2, y2 is 0.01. So now y3 will be y2 plus h times x2 plus y2. y2 is 0.01 plus h is 0.1, x2 is 0.2, y2 is 0.01. So this will be 0.21, 0.21 0.21 into 0.1 is 0.021 plus 0.01, 0.031. Next, we want to find at point 3. Okay, this is the one. Okay, this is y3, right? So for x naught, we got, for x equal to 0, we got y equal to 0. For x equal to 1, 0.1, we got y equal to 0. For x equal to 0.2, we got y is equal to 0.01. For x equal to 0.3, we got 0.031. So this is the answer. Okay. So next, the formula used to compute an approximation of second derivative. Observe, directly you can tell the answer is D. But if you are understanding numerical methods, the answer is straight away D. See, there is x naught minus h, x naught, and x naught plus h. This is not a differential equation problem, but how do you write the second derivative? Correspondingly, the y value is f of x naught minus h, f of x naught, and f of x naught plus h. The first derivative between these two is f of x naught minus f of x naught minus h by h. And the first derivative between these two, f of x naught plus h minus f of x naught by h. Now, derivative of these two. Okay, this is say this is, if you do forward Newton codes, so I need f dash second derivative f dash x naught minus f dash of x naught minus h by the difference is h again. So this will be f of x naught minus f of x naught minus h minus, sorry, f of x naught is this. So f of x naught plus h minus f of x naught by h minus f of x naught minus f of x naught minus h by h. So this is equal to f of x naught plus h minus 2 f of x naught minus plus f of x naught minus h by h square. So this is the answer. Okay, so very easy to see. See, this cannot represent a differential because there is no h and there is a plus sign. This can represent, but this is the first derivative only. Second derivative means h square has to come in the denominator. And if you observe this, there has to be a minus sign, all a plus. This cannot be. Okay, so just observing the formula, we can say that this is differential. This is the second derivative differential. Now let's look at the any other. Okay, there is a numerical problem in Runge-Kutta method. Let us see. So see the question. What is second order Runge-Kutta method? It is backward Euler method. Second order Runge-Kutta method is backward Euler method. And step size is 0.1. In the first step only, he is wanting us to calculate. So x naught is equal to 0, y naught is equal to 0, given. Okay. Now, in the backward Euler method, y1 is y naught plus h times f of x1, y1. What is this f of x? X minus y here. So y1 is y naught plus h times x1 minus y1. So I need to calculate y1. What is given? x1 is given 0.1. Step size is 0.1. So in single step I'll get. So y1 is equal to y naught is 0 plus h is 0.1 and x1 is 0.1 minus y1. So y1 times 1, this bring the y1 terms to the side, 1 plus 0.1. So y1 is 0.01 by 1.1. You get 0.009. Okay, to whatever approximation it is asked, we can do. If it is 3 decimal, third place decimal, it is asked. So answer is 0.009. Okay. Now let us look at the general questions. Oh. Okay. Let us do this match the following question. So we have to match the method with the purpose it is used for. Okay, now let us see. Newton-Raphson method. We know for what it is used. It is second order. It is used for solving equations. Okay. So solving nonlinear equation, solving linear simultaneous equation. No, linear simultaneous equation. We use matrix method. Solving ordinary differential equation, numerical integration method, interpolation, calculation of eigenvalues. No. So this Newton-Raphson method E matches with solving nonlinear equations. Okay. So E maps to 1. So E1. So we have these two options now. Second one, Runge-Kutta method F. It is solving ordinary differential equations. F3. So here we got the solution. You can cross check Simpson's rule, the other two. Simpson's rule is used for numerical integration. So G maps to 4. Gauss elimination is used for solving linear simultaneous equations. That is H equal to 2. So this is 4th. Okay. Let's match the following. Now let's look at another one. Another set of match the following. Okay. Matching again. Second order differential equations. Second order differential equations. Look at the other one. Non-linear. Actually, it is differential solving ordinary differential equations. You cannot say second order differential equations. This first order differential equations, we use Runge-Kutta method. There may be an error. Now let's see. Non-linear algebraic equations, we use Newton-Raphson's method. So Q maps to 2. Linear algebraic equations, we can use Gauss elimination method. R maps to 3. Okay. Numerical integration, Simpson's rule. So S maps to 4. So this should be, this cannot be second order, but anyway, P maps to 1 for whatever is left. So 1, 2, 3, 4. C is the correct option. Okay, so with this, I stop. You can, I have shared a book, link of a book. From that book, you can solve a number of questions related to this numerical methods. So with this, we finish numerical methods also. Okay, how to solve differential equations. That's what we cover. All right, thank you. For those of you writing exam tomorrow, wishing you all the best for the GATE exam.
Thank you, sir.
Go through